All right, you already heard Colonel Watts give her lecture with board problems, and she went over how to work some problems, but I just want to go over everything again so that you have it as a record. The first thing is, of course, she probably taught you about the multiplication rule. That's that if you have a number of elements after pairing m elements with n elements, that's going to be m times n elements. That's really the only rule as far as a mathematician is concerned, because everything else can be derived from this rule. We used this in MA 376, so if you just took MA 376, we used this to count the number of experiments where you had different factors. If you remember things like where we had 3 brands of popcorn with 2 microwaves and 3 locations, then you would have the experiment number 1 would be using brand A with microwave number 1 in the lounge. And experiment number B would be using brand A with microwave number 2 in the lounge, and so forth. So the way, if you were my section and probably the other sections, you probably drew what's called a combinatorial tree, where you would count the paths in the tree. So A, for example, the brand of popcorn could be paired with either microwave number 1 or microwave number 2. And then microwave number 1 could be paired with lounge, kitchen, and room, and so forth. And so experiment number 1 would be that path, microwave A with brand A with microwave number 1 in the lounge, and so forth. So then you count the number of paths. The total number of paths that you're going to get here is 6. But you also have to do the same tree for brand B and brand C, and there's symmetry in them. There's 3 trees. So there's 3 different trees I draw, times 2, they would have these microwaves, and then they would have the 3 locations, which gives you a total of 18 experiments. Somebody mentioned last time that a one-to-one function was something that was talked about maybe briefly in linear algebra. You talked about one-to-oneness, but you probably moved away from one-to-one function eventually and talked about things like row rank and column rank and things like that. So the formal definition of a one-to-one function is a function that goes from a domain S1 to range S2 with the property that if the y values are equal, then the x values are equal. This definition used to mystify me, but really it's easier to think of what we know from grade school and high school math, that something's not one-to-one if it fails the horizontal line test. So here we have 2 y values that are equal, but their x values are not. So y equals x squared is not one-to-one because the f of minus 1 and f of 1 equal each other, but the x1 does not equal the x2. So it's easier to understand this definition with a counterexample than an example. So that's the formal definition of one-to-one. So if I have a set with r elements in it, and they're all distinct, a permutation is defined to be a one-to-one and onto function that maps A to A. So it's just a rearrangement of these guys. The way we think of it is that onto means that everything in the range got something from the domain. Everything in the range is covered. So this function here is not to one-to-one on R because all the negative numbers were left out. Nothing can be left out on the range. Here, everything has to be covered. So N1 could say be mapped to N5, and then N2 could be mapped to N1, and so forth. Everything in A would get mapped to everything in A, and you're really rearranging them. So N5 is going to take N1's spot. It's a rearrangement of the domain. So again, here, when we talk about permutations, we intuitively think about rearrangements, but when I have to prove something, when someone tells me there's a permutation, what it means is there is a one-to-one and onto function from the set onto itself. Permutation formulas are used when order matters. So that means, like, for example, if I have A, B, C, that's different than C, B, A. Ordering those are different because I'm rearranging them. And the formula you need to know is that the total number of rearrangements of R elements, or the total number of permutations I have, is given by R factorial. That doesn't mean you say R very loud. Unfortunately, I did have an ex-boyfriend that used to think that this was an exclamation point. So if you have R factorial, you just say R really loud. Ex-boyfriend. What it really means is that you're multiplying everything from 1 to R. And the way we write it symbolically is we start with R, we multiply by R minus 1, R minus 2, and dot, 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 all the way to 1. If I have n elements, so that formula you need to know, just in case you have to build something from scratch. And the second formula you have to know is the permutation formula, which is in your book. That's when you have n elements, and I want to count as how many R element subgroups there are. So let me show you an example. This is example 2.8. The book is fabulous for examples. So this is taken from your book, Intro to Mathematical Statistics, or Mathematical Statistics. Take R equals 3. They have 3 employees drawn without replacement from 30 employees in a bowl. So they're going to take the names of 3 employees out where there's 30 employees. How many, if they're going to do this experiment, how many possibilities are in the sample space? Well, n factorial in that formula is 30 factorial, and n minus r factorial is 27 factorial. I didn't have a calculator. I was too lazy to grab a calculator. So 30 factorial is 30 times 29 times 28 times 27 factorial. So I just put them out like this, and then I can cancel them. And that leaves me with this gigantic number. You don't have to do that. You can just get on your calculators. Most of your calculators, I think the one that you're issued by West Point should have this on it. So the real question is, how do I know when to use this formula? Well, I'm looking for the number, the trigger words is that you're looking for the number of ways to make a 3-element group from 20 objects. So you're looking for the number of ways to make an R element group from n objects. That's how you have to remember. All right, so I'm going to stop this module here so that they don't get too long. This is just about multiplication rule and the permutation formula and examples.